So in this video, we're going to demonstrate what a bias resistor is and the basics of what it is doing inside your guitar pedal. So firstly, what is biasing? Well, in a lot of amplifiers, you can have dual supplies. In this scenario, our op amp here has a positive 9-volt supply and a negative 9-volt supply, we'll say. Because of this, we can reference the middle as 0 volts or ground. So the output signal of this op amp has half of the sine wave here above the positive voltage mark, and half of it is below the negative voltage mark, centering at 0, as mentioned just a moment ago. A guitar pickup works in the same way. As the string vibrates over a pickup, the interaction with the pickup's magnetic field generates a small voltage signal, and half of it goes into the positive voltage, and half of it goes in the negative voltage, centering at 0. Though this is a very small signal, so it won't be going anything higher than maybe a couple hundred millivolts peak to peak. However, when talking about guitar pedals, it is often that we have a single supply amplifier, where we have it being powered by 9 volts and ground, such as in the form of a bipolar junction transistor, a JFET, a MOSFET, or even an op amp. This presents a problem. With our pedal having its range of voltage go from 0 volts ground to 9 volts, instead of negative 9 volts to positive 9 volts, our single supply amplifier in our pedal cannot use ground as a reference for the center of the signal, as it would just slam the half of the signal into ground whenever it was going to the negative voltage side of that sine wave, clipping your signal terribly. So how can we fix this problem? Well, if we could somehow tell the amplifier that the center point of the signal, or the bias, is between 0 volts and 9 volts, then that would avoid the issue we just mentioned a moment ago. So what does that look like? Well, let's take a look at a simple op amp boost. Here we have a TL061 op amp acting as a non-inverting amplifier. Because of the values of R3 and R4, we can see that this amplifier has a gain of
11.
So if we go up here to simulate and then go to run, we're going to see here that we have a 250 millivolt peak signal here, or 500 millivolt peak to peak, at 1 kilohertz. See how this signal starts at 0 and then goes up to 250 millivolts and then goes back down to 0 and then goes down to negative 250 millivolts and then back up to 0 and so on. That's what one might see from a guitar signal with hot pickups with a high pick attack. So now if you look here at this op amp, you're going to notice to the left of it these two resistors here forming a voltage divider. They happen after the coupling capacitor here on the input, so that the input's AC signal makes it through and gets to this voltage divider. So let me just double click here. What you notice is our signal is now no longer being centered at ground. It's actually being centered at 4.5 volts. This is because R1 and R2 are pulling equally from the top, 9 volts, and from the bottom, ground. And because they're both of the same value, it's pulling equally, so it pulls it at the halfway mark. Halfway between 9 volts is 4.5 volts. Because it is at the halfway mark, like in a dual supply amplifier where it would have been ground, this bias voltage is sometimes called virtual ground. It's not at 0 volts, but it's acting like it is if this was a dual supplied op amp. Another thing to note too is these resistors here, R1 and R2, you typically want to keep them very accurate, so it's important to make sure that when you're populating those resistors that they have 1% tolerances or better. That way you have a lot more predictability on this voltage divider. So now that it is centered between 0 volts ground and 9 volts, we can amplify the signal. So if we looked at the amplification of this sine wave, you can see that it too is centered at 4.5 volts. But what were to happen if we didn't get this bias centered? Well, let's see what that looks like. If we were to change the value of R1 from 2.2 mega ohms to, say, 1 mega ohm, and let's go here and rerun the simulation, you can see that my bias is no longer centering at 4.5 volts, but rather somewhere closer to 6 volts. Well, so what? There's still room above and below the 6 volt mark for a 500 millivolt peak-to-peak signal. This is true. However, now if the signal gets amplified, you can see once it hits the rails of the op amp itself, it will clip, but it's going to clip unevenly or asymmetrically. If this were properly biased at 4.5 volts, which we can do here just by returning this resistor back to 2.2 meg and rerunning the simulator, you can see that the signal would have had enough headroom on the top and the bottom to not clip at all. And if this was intended to be a clean boost, this is probably how it should have been done, not with an uneven bias. Now let's take a look at another example of biasing. Just like before, we have a non-inverting op-amp with a gain of
11.
However, this time we move the voltage divider from over here into the power supply, and then used a single resistor to pull the input signal up to bias. This is useful as if you have multiple op-amps that need to be biased, you don't need 2 resistors per op-amp like in the previous example, but rather just one. And this one resistor right here is what you typically hear people call the bias resistor in pedal design. Now, I've been harping on biasing the signal at 50% of the main voltage a lot, but this also isn't a rule. In the case of overdrives, distortions, and fuzz pedals, setting the bias closer to ground or towards the 9-volt rail may be desired. For example, let's take a quick look at a germanium tone bender Mark II. So here in our tone bender, let's go to simulate. You can see we have our regular input signal centered at 0 volts coming from our guitar. But as it leaves the Q1's collector pin here, you can see that it's being heavily slammed to the 9-volt rail. Finally, at the output of the pedal, we can see that we have a heavily fuzzed signal, but it's leaning more towards the 300 millivolt positive voltage rail than it is down here at its negative 150 millivolt negative rail. However, this is the signature sound of a tone bender Mark II, an asymmetrically biased fuzz signal. So there you are. This is what biasing's all about. The idea is simply, where do you want your center to be? So I hope this helps in the understanding of what biasing and bias resistors are doing in your guitar pedal. I did leave out that they also contribute to the calculation of input impedances, but that's a topic for another video. Anyways, that's it for now. If you like these kind of videos, press that like button, and if you haven't subscribed, please subscribe. If you wish to help support us making more of these kind of videos, please check out our web store at www.diyguitarpedals.com.au and check out our pedal kits and PCBs, as that would really help us out. Anyways, thanks for watching. Cheers.